Methods for handling deadlocks. So how we can handle or deal with a deadlock situation. There are four strategies that can be used to deal with deadlocks. The first of these is ensure that system will never enter a deadlock state. In the first scheme, it will be ensured that deadlock state never occurs in the system. So we can use two policies to avoid a system to enter in a deadlock state. The first policy is deadlock prevention, and the second one is deadlock avoidance. The next strategy is to allow a system to enter a deadlock state and then recover. So this scheme, it allows the system to enter a deadlock state. Unlike the previous scheme, which ensures that system never enters a deadlock state, this second scheme, it allows a system to enter a deadlock state. And once a system is in a deadlock state, then it will recover the system from this state. The third strategy is ignore the problem. That is, ignore the problem of deadlock and pretend that deadlock never occur in the system. Though we are pretending that deadlock has never occurred in the system, but they may occur in the system. And if they occur, what will be the consequences of this third approach? So these are the three major strategies to deal with deadlocks. Let's start with the first one. Deadlock prevention. That is how we can prevent deadlock from occurrence. As we have discussed before, that there are four necessary conditions for a deadlock to occur. These conditions are mutual exclusion, hold and wait, no preemption, and circular wait. So these four conditions must exist simultaneously for the presence of deadlock in the system. So how we can prevent deadlock from occurrence? We have to invalidate one of the four necessary conditions for deadlock. This means at least one of these four conditions must be invalid. It must be false. And if at least one of these four conditions is false, this means we have prevented deadlock. The first condition was mutual exclusion. Mutual exclusion means that processes, they can acquire resources exclusively if the resources are not shareable. However, mutual exclusion condition is not required for shareable resources. As we discussed earlier, that some resources are shareable while others are not shareable. For example, read-only file. These files can be shared between multiple processes. So this is a shareable resource. Similarly, printer can also be a shareable resource because a printer can be shared between multiple systems and multiple users. So mutual exclusion condition is not required for shareable resources. However, it must hold for non-shareable resources. Some resources are non-shareable. And for these resources which are not shareable between processes, then mutual condition, it must hold. The next condition is hold and wait. Hold and wait means that a process is holding a particular resource and it is waiting to acquire another resource, which is held by another process. So we must guarantee that whenever a process requests a resource, it doesn't hold any other resource. This means to invalidate this condition, what we can do, we can guarantee that if a process is requesting a resource, then at that moment, this process shouldn't hold any other resource. So it cannot do that it is holding a resource and it is waiting for another resource. It must release its available resources, the resources which are being assigned to this process. And once it has released all those resources, and this means it is not holding any other resource, then it can request another resource. Now it requires processes to request and be allocated all its resources before it begins execution. How we can achieve this? The first case is that processes may request that which resources they need for their execution. And all those resources can be allocated to the process before this process starts its execution. That is, during its execution, it will not request any more resources because this process has already mentioned its demand for the resources, and all those resources have already been allocated to this process before it begins execution. So during execution, this process will not be waiting for any resource, or it will not be requesting for any more resources. Or allow processes to request resources only when the process has none allocated to it. This means the second case is to invalidate this condition is that allow a process to request resource only when the process has no resources allocated to it. Only that process is allowed to request resources. However, these approaches, they leave us to this situation that is low resource utilization. So in this case, starvation is also possible. How starvation is possible? Because as we have said that if this is the case, that process has been allocated all the resources before it has started its execution. So if the resources have been allocated to a process and another process is waiting for the resources, it might wait for a long period of time if this first process is not releasing the resources, if it is not completing its execution you can say in a short period of time. So in that case, the other processes, they may have to wait for a long period of time. So starvation is possible if we invalidate hold and wait condition. And how it leads to the low resource utilization? Low resource utilization means that as we have allocated all the resources to a process before it starts its execution, however, process doesn't need all these resources at once. It may need these resources at different time intervals. For example, a process may need printer at the last moment of its execution when it is going to finish, because then it may need to print the output to the user. So printer has low resource utilization because all the time when the process was executing, this printer was exclusively used by this process. Though it was idle, it was not being utilized. However, the process has been having the control of this printer. So it results in low resource utilization. The third condition was no preemption. No preemption condition was that a process will voluntarily release the resource. We cannot forcefully take the resource back from a process. So if a process that is holding some resources and this process requests for another resource that cannot be immediately allocated to it, then all the resources currently being held by the process are released. This means if process is having some resource and it may need additional resources, and the request for these additional resources cannot be granted because might be these additional resources are being held by other processes. So what we will do, if the request cannot be granted immediately, we will take back all the resources that has been allocated to this process. So we will forcefully take the resources back from this process. Preempted resources are added to the list of resources for which the process is waiting. And the resources which have been preempted means the resources which have been taken back from this process. These resources will be added to the list of those resources for which this process is waiting. Because we have taken these resources from, say, a particular process. So this particular process will need these resources as well as the resource which it has requested. It need all these resources. So all these resources will be added to that list for which this process is waiting. The third scenario is process will be restarted only when it can regain its old resources as well as the new ones that it was requesting. So process will restart only when all of this list becomes available. That is, all the resources in the list, they become available. And what is this list? This list contains old resources which have been preempted from the process, as well as this list contains the new resource that this process was requesting before we preempted this process. The next case is circular wait. Circular wait means that processes exist in a circle and these processes are having some resource and they are waiting for the resource which are being held by the next process in that circle. So in this way, a circular wait condition exists in this system. So how we can invalidate this condition? We can impose a total ordering of all resource types and require that each process request resources in an increasing order of enumeration. This means resource types, they will be assigned some order, some particular order, that in which order resources can be requested. And resources will be allocated only in increasing order of enumeration. For example, we may impose the order that a disk drive, it will be allocated before tape drives. So disk drives, this resource type has order which is earlier than the tape drives. Now, if a process is requesting both tape drives and disk drives, we have to ensure that we allocate resources to this process in increasing order of enumeration. That is, first, disk drives will be allocated because they have order which is above the tape drives. So disk drives will be allocated. And once the process has finished with disk drives, then we can allocate tape drives to this process. Invalidating the circular wait condition is most commonly used. Another way is simply assign each resource a mutex logs, which is a unique number. This is what I have said, that we will assign disk drives a unique number, and similarly we can assign tape drives another unique number, and processes they can request a resource only in increasing order of number. So resources must be acquired in a particular order. Deadlock avoidance. This strategy requires that system has some additional prior information available. And what is that prior information? Simplest and most useful model requires that each process declares the maximum number of resources of each type that it may need. This means before a process starts its execution, it must declare to the system that which resource type it may need during its execution, and what will be the maximum number of each resource type that it may need. For example, if a process needs printers, tape drives, and disk drives during its execution, it must declare to the system that it needs these three resource types. And it should also declare that how many instances of each resource type it may need to complete its execution. So it must declare this information before it starts its execution. That's why we are calling it a prior information. The deadlock avoidance algorithm dynamically examines the resource allocation state to ensure that there can never be a circular wait condition. Now, we will use a deadlock avoidance algorithm that will check from time to time that resource allocation state ensures that there exists no circular wait condition in the system. That this means whenever a resource will be allocated to a particular process, an algorithm will be used. This algorithm will ensure that allocation of this resource doesn't uh, put a circular wait condition in the system. Resource allocation state is defined by the number of available and allocated resources. And what is this resource allocation state that algorithm examines? This resource allocation state is number of available and allocated resources and the maximum demand for these resources by the process. So these three criteria determine the resource allocation state. That is the number of available resources in the system and how many of these resources have been allocated to the processes and what is the maximum demand of this process uh, for this particular type of resource. Save state. When a process requests an available resource, system must decide if immediate allocation leaves the system in a safe state. So if a process is requesting some resource and this resource is available, system can allocate this resource. However, before this allocation is made, system will ensure that if this resource has been allocated to the process, will it leave the system in a safe state? A system is in a safe state if there exists a sequence of processes, that is P1, P2, P3, and Pn. These are all the processes in the system such that for each Pi, the resource that Pi can still request can be satisfied by currently available resources plus resources held by all the Pj. This means, for example, if P2 is requesting for some resources, then system will ensure the safe state by examining that the request of P2 can be fulfilled from the available resources as well as from the resources which are held by P1 because j is less than I. If this is P2 is our current process and then this is P1 is the Pj process. So request of the P2, it should be fulfilled by the available resources as well as by the resources which are being held by the P1. So if this is the case, then system is in safe state. Hence, if P1 resource needs are not immediately available, then Pi can wait until all Pj have finished. This means if the request of a particular Pi process cannot be uh, granted immediately, in that case, Pi will wait. And For how long it will wait? It will wait until all the PJ have finished. And when the PJ processes, they have finished their execution, what they will do, they will release the resources. So once the resources become available and they are released by the PJ processes, they can be allocated to this waiting process PI. When PJ is finished, PI can obtain needed resources, execute, return allocated resources, and terminate. When PI terminates, Pi plus 1, I plus 1 can obtain its needed resources and so on. So once, for example, if this process terminates, P2 terminates, then the next process, which is P3, that process can obtain its required resources and it may proceed with its execution. So under this strategy, if a system is in safe state, then it means there are no deadlocks. That is, whenever a process will request resource types, system will check whether the resource allocation will leave the system in a safe state or not. If it finds that system will be in the safe state, then this means no deadlock will occur if the resources will be allocated to this requesting process. However, if a system is in unsafe state, that may indicate the possibility of a deadlock. And if there are deadlocks, in that case, we will use avoidance algorithm. Avoidance algorithm ensure that system will never enter an unsafe state. So this figure explains the safe and unsafe states. Safe states are all those states which mean deadlock will never occur in the system. Allocation of the uh, resources can be allocated to the processes in a safe manner. Whereas presence of unsafe state means that there is a possibility of deadlock. This shows that in unsafe scenario, there are some states which doesn't lead to the deadlock. And some states, as this rectangular box gives the idea that some states from this set of unsafe states, they may lead to deadlock situation. In other words, it doesn't mean that all unsafe states can lead to deadlock. Only few of the unsafe state can lead to the deadlock.